All right. Rick, really, really nice to have you on the show. I had you on the podcast already, on the Synera podcast, now in a deep dive session. Today, ladies and gentlemen, it's all about Meshless FEA, simplifying, simulating, and succeeding with Meshless FEA. And I think without further ado, Rick, let's get started and let us know what Meshless FEA is all about.
Yeah, thanks, Jousef. Thanks for having me again on this deep dive. Appreciate it. Appreciate everybody's time as well. And again, good afternoon, good morning, good evening to everyone. And yes, let's do a deep dive. There were a lot of S's there. Jousef just threw out. So let's start with the M, which is meshing, right? So, all right. So this, as you can see, this is Synera, the canvas. So Synera, if you don't know, is a process automation platform, and the keyword here that we focus on is automation. And in automation, if you have to go through meshing steps or tinker manually, you break automation, right? So meshing essentially breaks automation. So what we have done for FEA is eliminate this whole meshing step. And today, what I'm going to do is kind of walk you through like a basic, in a traditional FE, what you go through, right? You already know, but I just want to kind of recapture that and show you where, Intact comes in and how we can kind of help accelerate the simulation process for you. So let's just start up. So typically, you're this. So first of all, there's a very simple part, right? We're starting with a simple basic bracket where we're going to fix one hole and then put the load on one hole on the other one and then run an analysis on it. But even with the simple analysis, you can see kind of the differences between the traditional way of doing it versus how we've been doing it. By the way, Intact has been around for over 25 years now, but we recently started kind of commercializing this mesh-free technology. All right, so first, again, you either create your model or you import it from somewhere, some CAD software, right? And step two is usually the meshing step. So here you can see, and Synera does a very nice job of showing you the times right away. So, I don't have to go and to calculate those for you. This meshing, this bracket took about 2 minutes, 20 seconds. And we set the element size kind of big in there because we don't need it so big, right? So it's a simple part. And then you set, typically you would set up your material properties and your kind of load cases, the pressure load and restraint load. And then you run the solver. So we're running solver 41 seconds. Hey, that's really good. Right. That's pretty good. It's fast. So, 2 minutes and like 45 seconds or so, like around 3 minutes. So, okay, that's not bad. I can wait 3 minutes to look at my results and everything. So let me hide this geometry so you can see the results. So this is a displacement results. You can keep your eye on this number, 1.198. That's your max displacement. So, okay, what's the big deal then? Why do we need Intact? And, that's what I'm here to show you. So I'm going to remove this. So with Intact, what we're doing is really simplifying the process. So Intact lives as a module within Synera. It lives in the FEA tab. You have in the model section, you have your component. Under solvers, we have our modal solver and stress solver. So a quick way to find things in Synera is also to double click and then type it in there. So here you go, Intact component. So we always have to bring our component in, which is the, kind of combines the geometry material. And here you can also right click. And if you wish, you can open example, show help. If you want to learn more, you can copy and paste these things, right? So we have all the help and everything's built into this. So I'll go back to this. So, okay, we have our Intact component block, and then we're gonna add our solver block here. So give me 1 second. Synera decided to freeze on me for a second. There we go. You know how live demos go, right? There we go. Intact solver. Okie doke. All right, so what we're gonna do is we're not gonna, I'll just leave all these meshing nodes in there. I'm just gonna add the geometry here and the material to my component block. That's ready to go. Then I'm going to add my loading conditions to the intact solver, and also the component to that. So the simulation has started now, and I'll set it to 100,000 resolution. So the resolution is kind of your target number of cells that we want to go after. 12 seconds, simulation is complete. Now let's analyze that result. I may view the model, put that link in there, and it will show up here in a second. Oh, I should set the results. We want to look at the displacement. And yeah, default, that's good. Oh, why is not showing up? Let's try it again. I just did this test, that's odd. Nodal displacement, let's look at the stresses. No, it's good. All right. I'll come back to this one. That's kind of strange that the result is not showing here. Me. That's weird. All right, well, this was a basic example anyway. But anyways, the result, the point is the max displacement is still 1.198. That's very strange that it didn't show up. There was some weirdness happening. Let me go on to the next example. I can come back to this one. If this continues, I can restart this program. All right, so let's go on to another example. So this one, let's open this up. All right, this one is an airframe stiffener panel, right? It's a pretty complex. Typically, you see an ISO grid on this panel, but this one we decided, hey, let's go kind of crazy with this Voronoi pattern, and you can see there are many small features. There are these bigger holes. So there's a lot going on in this model, right? Then let's look at some results here. So again, for meshing, this one took about 15.5 minutes to mesh. Then you set up the problem. Then you run the FEA solver. Took about 4 minutes to do that. So, all in all, about 20 minutes or so, right? And let me visualize this one. Let's see. Oh, okay, that visualization works fine. Okay, so I'm gonna hide that visualization again. Again, on this one with one element size, the nodal displacement was 2.978. So here are some stats that we did, right? We started out with a little bit larger, 1.25 element size. Displacement was 2.46. Took about 15 minutes. Again, changing that one around 3. This was the displacement about 20 minutes or so. So then let's go to intact. So intact, again, we had the same problem set up. We're using the same material properties and boundary conditions. And we have the intact block, the intact stress block. And I'm just going to connect. And we're set this to a lower resolution, 50,000. So let it run. So hopefully this time my machine shows, maybe on the display, shows this time. So we're waiting. This takes about a minute or so. So in the meantime, while this runs, um, you know, so with Intact, what we're focused on again is simplifying the simulation workflow, as you saw there, right? So we're we're not going through the meshing step. We don't have to go through all these cumbersome steps, painstaking steps to get to the analysis, right? Because meshing doesn't. It's meshing is an iterative process, right? It's again, it's not an exact science either, and you have to consistently make these trade-offs for quality and accuracy and speed. Um, and if you go Google like the art of meshing, like there's countless articles, right, on what settings to use, how to mesh, and so forth. All right, this is done. Took about a minute.
We had one question, Rick, from the audience. Maybe we
Yes,
can answer that already.
right.
Is the meshing done on the surface geometry or 3D geometry?
That's a great question. So this one, the visualization showed up. So all right, so the meshing is actually what we're doing is meshing the background, so meshing the space around the geometry. Right, the Intact technology is based on the immerse method of moments, which what it does is if you watch the podcast, it's we take the geometry, we immerse it in this 3D grid, and then that 3D grid, you can think of it as like a 3D graph paper that intersects the geometry, and that's when we do our calculations on the boundary. So let me hide this guy.
You mentioned meshing and meshless. How are they compatible, these two terms? Because someone in the LinkedIn comments asked, he didn't understand it because it's about meshless FEA, but we're still meshing somehow. So how does that fit?
So the word meshless is kind of not the right term. It's really should be no meshing, right? The process of meshing is what we're eliminating, right? What we do is this our Intact technology is based on classical FEA methods, where we are using the same classical methods in performing FEA on the non-conformal mesh. But what we do is mesh the kind of the space around it, so we can. This allows us to take the geometry in and out. Like we put a different geometry and keep the same kind of boundary conditions and these properties in there.
Got it.
And quickly on this, right? So our max displacement was 2.923, and what did I say here? After 20 minutes, after 30, about 20 minutes or so, 2.97. So it's like within 2% or so, right? And at a fraction of the time, this is 20 minutes versus 1 minute, right? So that's the results, are getting to the same. And this is a fairly complex part. Go back to this guy again. I'm still not sure why this. I may have to restart this particular one, but that's okay. Oh, there it is. So yeah, that I wanted to show you this that 1.198 number, the max displacement, and this simulation was done in 12 seconds versus the traditional way was like 3 minutes almost. So okay, now let's kind of I mean I went through those pretty fast. I thought they would take longer, to be honest. But our simulation is quite fast. But hey, we can spend more time on Q&A as well.
There's some follow-up question regarding that. Rick,
Yeah.
because we mentioned you answered the question of is it done on the surface geometry or 3D geometry. He wants to understand if the stresses inside the material is also being calculated right here.
The stresses inside
of the material, yes.
Talking about the inside the geometry. It's like take a cross section, like inside.
Probably, yeah. This is
to
what I
visualize.
understand.
Yes, yeah. You can do that. So I personally am not so great at Synera yet. I'm working on it. I just started learning this a month ago. So, but there's ways to cross section the model, and then you can assess the results. We can resample your analysis. So what we do with Intact is we have with our background grid that we create, we can query that information, right? We're essentially querying this geometry for, or the analysis space for the information that the user may want, the insights the user may want. Then let me show you an example of that. One second. I have a couple of pictures so to show you what's happening. So if you can see this picture, so this right here is that first example. This is our the geometry that's immersed in the grid, right? And we're taking, this is how we analyze it. And if you want a deeper, close up view, is kind of looks like this. So it's like that 3D graph paper that I had mentioned. And so with this information, and it's inside, outside, not just on the surface, we're able to go in and query this model for the data that information that you're looking for.
Super interesting. There's a couple of questions. One being, what is the error comparison with respect to meshed methods? I think we answered that partially. It's still a meshed method, but how is it comparing in terms of errors?
So as you can see, we do convergence studies, right? And this is like a quick convergence study. But we do more detailed convergence studies, and we have a lot of benchmarks against the standard NFM's problems, like beam plate, these type of problems as well, that we've done, and we can happy to share those with anyone that may be interested in this. And typically, I would say it's our stress results, our displacement results are within 1 to 3%, and our stress results are typically within less than 5%, and all this in a fraction of the time. Again, you can increase just like in traditional way, like the element size, we can increase our element size, the resolution, to get to that converged results, right? It's just a matter of going through that workflow.
That makes sense.
Yeah, I have one more example.
One follow-up question?
Yeah, go ahead.
Maybe you ask the question now. How efficient is the software or like the workflow compared to ANSYS or Abacus?
Well, I mean, as you can saw, the efficiency, right? We're in Synera, there's the module is built in right there, so you don't have to leave the Synera platform for to use Intact. Once you have the problem set up, it's just a matter of computing it, right? So it's very straightforward. Like as you can see, like we have just two components, these blocks that or nodes that you can use to set up the problem. And even in the solver block, right, we have all the different settings that you may be interested in. The element type, the solver type, direct versus iterative. These are some of our advanced settings. If you if you know the cell size of your geometry, you can use that cell size as well. So with this, typically, the system will select the cell size if you have selected both resolution and cell size. So resolution is kind of your target number of cells that should work, so that you think it should work. So you have these kind of additional tools that you can do, and the efficiency is the simplification of it, right? And also the speed of it. We don't have to go and tinker and get the mesh right, because we can do our analysis on a very coarse results and get you 80-90% of the way there within seconds, or we can take this use the compute resources to get to the full validation level. It just depending on the kind of the compute resources that you have available. And one thing I'd also add is that our solvers are they're currently CPU based, right? These are not GPU solvers that we have developed, right? These are CPU, and I'm using a pretty standard laptop. It's not a workbench or anything. I'm running this on a laptop. I think I have 32 gigs of RAM. It's an i9 processor. But a lot of our customers have these super duper heavy machines that they're running these analyses on, and it's almost instantaneous that they can get the results in. So that's fascinating to see.
Yeah, that's also something good that you mentioned this, Rick. Someone in the comments is actually asking, could you provide details about the computational resources being utilized?
Right. So yeah, as I mentioned, like those are the compute resources that I have. But we can use so we can set the threads. We can use it's multi-threaded for CPU, but you can also in here you can specify how many threads you want to use, and we kind of give you the complete flexibility and control of how you want to kind of optimize your own simulation workflow.
Hmm?
All right. I'm going to go to my last example here. So this is an engine block. Let's look at this model first.
Beautiful.
Yes, this is a beautiful model. As you can see, it has a lot of features, has a lot of parts, and obviously meshing breaks with this one. Well, I mean, you can mesh it. So for reference, we had one of our partners run this analysis in Nastran. They meshed it and solved it to do this. Most applications you're not going to be able to do that. It took I think 2 hours and 45 minutes to mesh, and it was a kind of they used a hex meshing. It wasn't a tet mesh; it was a hex mesh. Excuse me. And then the solving took another 45 minutes or so. Yeah, so it's like over 3 hours, right? Just to analyze this part. Typically, what you'll have to do with this part is you have to simplify it, right? You have to remove all these small features, maybe some of these holes as well. So right. So let's see what Intact is able to do. So I have again set up the material properties. So what we're doing is we're fixing the bottom and putting a pressure load on the cylinders, and then I'm gonna set this to a 200,000 resolution, and I'm gonna get that. Now it goes. So I actually can't remember how long this takes. Maybe about a minute or so, just to get to the 200. So as I was saying, this is a coarser resolution we're doing. So just a quick feedback, but then we can start expanding that as well. And again, this is happening. This is real time, right? We're on this live setting. My computer resources are being my laptop resources are being used for that. It's running a pretty heavy simulation. This very complex geometry at the same time, right? So let's give it like a minute or so, and then see where we end up. In the meantime,
Sounds good.
we
We had one question regarding the boundary conditions. So how are the boundary conditions being set up?
Sure.
In this case,
yeah, I can go over that. So here I can. Okay. Analysis. Let me finish this analysis. I don't want to mess up the thing, and then I can answer that question. But typically, it's like a fixed displacement. We set the restraint, and then okay, it's done. 1 minute and 13 seconds. This took. So yeah. So real quickly under restraints. So I can make it visible. Hide this guy. I'm gonna hide I'll leave the model on, it's fine. So basically, if you can see, we put a fixed constraint on all these holes in the bottom, and then these cylinders have a pressure load, 20 magnitude of 20, and yes, and then we combine that gets to the load, and then we see the results here. Hide this so you can see it. Right. This model kind of gets a little heavy because it has there's a lot of data in it. but anyway, so that's the kind of the idea. And then here, once it's done moving around, I will show you what I did. It's like a very quick, convergence study. If I remember correctly, I set this to, right, initially it's 200,000 elements. Then I set it to 1 million elements, and that that took things like 3 minutes or so, and then bumped that up to 1.5 million elements, and then 1.8 million elements. So it started converging around 1.5, 1.8 million elements, and that took about 10 minutes for a part like this. Um, and the 1 million element, it was, let me have it here. Yeah, the 1 million element, 3 minutes was within 7%. And 1.5. Okay, I did 1.75 and 1.85. So 1.85, 75 is when it started. You start seeing the convergence, and these are all like 10 minutes, 11 minutes. But you can see
Pretty sick.
within like 7%, within 3 minutes, we're able to get to that. Any
Pretty cool.
yeah, it's really, I mean, to be able to analyze a model like this in basically in real time, like, as we're speaking, that's pretty amazing. Even
It's
I get
pretty
surprised
nice. I
by
love
that.
that. We had a couple of questions. In terms of comparison, I think a lot of people want to know, like, how does it compare to ANSYS, Abacus, SimSolid? I mean, is the comparison even valid, or do you see more value in using something like Synera? Because we talked about the whole process automation bit, right? Where do you
Right.
see the value as just saying, I'm going to compare X with Y?
Sure. I mean, you can, like, a lot of our customers, that's what they want to do at first, right? They want to compare what our results look like with anybody else's results, and you can certainly do that. Synera is a process automation platform, and what we're trying to show the world here with Synera is that, the meshing really breaks down the automation aspect of it, right? So now we can put these simulations in a loop. We can put this in a loop. We can automate. We can do design space explorations without having to go through these meshing steps, and that's the beauty of Synera, right? But in Synera, you can also connect to ANSYS and Abacus, and you can do that. You can set up this problem with Intact, run through this DOE experiments, and then you can go to Synera, or go to ANSYS if you like, or if you want to compare those results as well. We can certainly do that. So here we're focused on, at least in the Synera platform, about kind of this automating simulation, especially to run these DOEs. You're able to do that, and these are just typical, pretty standard prismatic parts with small features. That's what we focused on today, right? So let's add another layer of complexity here by introducing lattices, right, or implicit models. Synera is able to interact with these lattices and these different types of geometries, and typical FE solutions, they are not able to kind of handle that, right? But Intact can. We can analyze on complex geometries like lattices, and you can even set up with different tools here where you're changing your lattice type or some lattice parameter, and then the simulation is updating instantaneously, right? So that's the value. At least that's what we see, and that's what our
Yeah.
customers are using it for.
Yeah. There's a question probably related to both. Are you providing a trial period?
Yeah, so Synera has, I believe it's a 14-day trial. You can reach out to them. Actually, that should be correct.
Let me just send the link. I'm going to send the link in the meantime.
Yeah. Also, I want to show you this. You can find, this is a Synera marketplace. Intact lives in it. Intact simulation is there. You can just download once you have access to it, you can download, log in, and you have Intact, and you can basically get this into your add-ins, right? Tools, there are all the different add-ins, I only have intact simulation, right? So
Nice.
but you typically have a list of add-ins in there. So yes, so Synera has a trial period, and intact again is a module within Synera, so you automatically have access to that through Synera. And then for Intact itself, we have some other plugins and that we work with other platforms as well. Intact is a very flexible tool. We have our own kind of standalone headless version with a Python interface, right? So it's called PyIntact. You can integrate that with existing software stack that you may have to run these DOEs in a headless way. And then we have our products in integration with NTOP, also in Rhino Grasshopper. So it's a very flexible way of accessing Intact simulation.
Really nice. I love that. Rick, thanks so much for the presentation. Let's just check for any open questions in the chat.
Hey, look, we made it in the right good time. That's perfect.
Yeah, that's pretty good. Nice. So I've sent a ton of links in the chat, ladies and gentlemen. If you want to check them out, check out intact-solutions.com and also synera.io for more information. I think we pretty much covered all the important questions. If you have any more questions, how can people reach out to you, Rick?
Fantastic. So on LinkedIn, you can reach out to me directly, right? I'm there somewhere. You can leave a comment on, continue to leave comments on this in the webinar there. We can reach out, or you can go to our website. I think you said we posted that in the chat, right? So intact-solutions.com. I think there's a link to connect with us. Several ways to connect with us, and we're always posting, videos and content on LinkedIn about the different ways you can use Intact. So just keep a lookout, follow us on LinkedIn, and reach out anytime you you want, and happy to chat more. This is a kind of it was a deep dive, but we can go deeper as well, and more one-on-one if you're interested.
Excellent, Rick. Again, thank you so much. Hopefully there will be another session in the future. And yeah, if people have any questions, feel free to reach out to me and or to Rick. And then I'll see you in the next deep dive, ladies and gentlemen. Have a good one.
Thank you, Jousef. Thanks, everybody.